We interact with water like every single day,
Right, absolutely. We drink it, we wash our hands with it.
Right, we rely on it to basically stay alive. But if you actually stop and look at the invisible ingredients that make up a single drop of water, you run into this totally mind-bending
It
paradox.
really is wild when you break it down.
Because water is made of hydrogen and oxygen, right?
Yeah.
And hydrogen gas is, well, it's highly combustible.
Extremely. I mean, just look at the Hindenburg disaster.
Exactly. That was a giant balloon filled with hydrogen gas, and it was incredibly explosive. And then, you have oxygen.
Right, which literally supports combustion.
Yeah. If you want a fire to burn hotter and faster, you just pump pure oxygen into it. But then when you combine these two highly flammable, fire-loving elements,
You get water.
you get water. A liquid that we literally use to extinguish fires, it makes no sense.
It completely defies our everyday intuition, you know.
It really does.
You take two things that possess this, like chaotic, fiery potential, and you snap them together at a microscopic level, and suddenly you have the ultimate fire extinguisher.
Which is just crazy to think about.
It highlights this really fundamental truth about the physical universe. When elements combine chemically, they don't just blend their properties.
Like mixing blue and yellow paint to get green.
Exactly. It's not like that at all. They create something entirely fundamentally new. The original identities of the hydrogen and the oxygen are completely overwritten.
Wow. So to understand how that is even possible, we really have to look at the invisible accounting system that governs the universe.
That's a great way to phrase it.
So welcome to this deep dive, everyone. Today our mission is to become like intelligent beginners in the world of atomic chemistry.
Yes, we're going to deconstruct the foundations of matter for you.
Starting from everyday ingredients we can see with our own eyes and moving all the way down to the strict mathematical laws that dictate how every single atom behaves.
And we have a really fun roadmap for this. We'll explore how matter changes, the mathematical laws those changes obey, and the brilliant historical minds who figured it out.
And we'll get into the actual mechanics of how atoms bond. Right?
Oh, absolutely. And don't worry, we are going to break down every single technical term step by step. No one is getting left behind.
Perfect. Okay, let's unpack this. I want to start with something that seems incredibly basic, but is actually the cornerstone of all physical science.
The difference between a physical and a chemical change.
Yes, there is a massive fundamental difference between those two things.
And the line between them is really all about whether the fundamental identity of the substance has been altered.
Okay, let's make that tangible for the listener.
Sure. Imagine an industrial desalination plant or, even just a simple kitchen setup.
Just a digital scale on a counter.
Right. You take that digital scale, you place a large glass beaker on it, you zero it out, and you pour in exactly 500 grams of pure distilled water.
Okay, 500 grams of water.
Then you take 50 grams of common table salt and you stir it into the water until it completely dissolves.
So it basically vanishes from sight.
Exactly.
Yeah.
But you are witnessing a physical change.
Because the salt is still salt. Right. And the water is still water. They've just kind of mingled.
Precisely. Their chemical structures remain entirely intact.
Like if I were to boil that water away on a stove, the solid salt would be sitting right there at the bottom of the beaker.
Exactly. And the most vital observation here, the really important part, is what happens to the mass.
The total weight of the materials.
Right. If you look at the digital scale, after the salt has vanished into the water, the display will read exactly 550 grams.
Because 500 plus 50 is 550.
The mass of the final solution is perfectly equal to the sum of the water and the salt. Nothing was lost into the ether.
And nothing was mysteriously generated either.
Right. And this holds true for literally any physical change. If you take a massive block of ice weighing 1 ton and melt it into liquid water, that liquid will weigh exactly 1 ton.
Okay, that makes sense. But, I struggle with this idea when we move into chemical changes.
Yeah.
Because honestly, my own eyes constantly lie to me.
What do you mean?
Well, let's say I'm sitting around a campfire, right? I start with this massive, heavy oak log that weighs maybe 20 pounds.
Okay. A nice big log.
And I set it on fire, which is a chemical change, right? A combustion reaction.
Yes, definitely a chemical change.
So I watch it burn for hours. And at the end of the night, all I have left is this tiny pile of flaky ash that weighs like maybe a few ounces.
Right. It looks like most of it just vanished.
It feels entirely obvious that the fire destroyed the mass. 20 pounds went in and a few ounces are left. The matter just disappeared.
Is the most intuitive conclusion in the world, honestly. And it's exactly what brilliant philosophers and early scientists believed for centuries.
Because it just looks so obvious.
They really thought fire was a process of destruction, a literal unmating of matter.
Right.
But we have to look at the broader environment.
Okay, how so?
It's what scientists call the difference between an open system and a closed system.
Oh.
The campfire is an open system. When that oak log burns, the complex carbon molecules in the wood are reacting with the oxygen in the air.
So it's not just the wood acting alone.
Right. And the resulting products aren't just the ash you see on the ground. The vast majority of the wood's mass is actually being converted into carbon dioxide gas and water vapor.
And because I'm sitting outside in the woods, those gases just float away into the night sky.
Exactly. The mass didn't vanish from existence. It just vanished from your immediate vicinity.
Right. If we wanted to prove this, we would have to, I don't know, enclose my entire campsite in a massive, magically heat-resistant, impenetrable glass dome.
Before you struck the match.
Yes. So that would be a perfectly closed system. We would weigh the log, the match, and all the oxygen trapped inside the dome.
And then you light the fire. The log burns down to ash. The smoke billows up. The gases fill the dome.
And if we could somehow place that entire glass dome on a giant cosmic scale,
the total weight before the fire and the total weight after the fire would be identical.
down to the final decimal point.
Down to the final decimal point.
You know, it's like a piggy bank.
Oh, I like that. How so?
If I take a ceramic piggy bank full of coins and I smash it with a hammer out on a balcony and a bunch of the coins go flying over the edge into the street, I have less money on the balcony.
Right, your local mass decreased.
Yeah, and someone might look at that and say, well, smashing the bank destroyed the money.
But no, the money just escaped your local area.
Exactly. However, if I put that same piggy bank inside a thick, sealed plastic bag and then I smash it with a hammer,
Oh, right.
every single coin, every piece of ceramic shrapnel is still trapped in that bag. The total weight of the bag doesn't change by a single gram.
Even though the internal structure of the piggy bank is completely chaotic and different now, that analogy maps perfectly onto chemical reactions. Yeah, whether you are dealing with a campfire, an internal combustion engine in a car, or an industrial chemical plant, you are basically just smashing piggy banks inside sealed bags.
The arrangement of the material changes drastically, but the total amount of material remains eternally constant.
And we can actually see this modeled in simpler, real-world laboratory setups without needing a magical glass dome over a forest.
Oh, right. I've seen this done with standard baking ingredients.
The balloon trick?
Yeah, the balloon trick. You take a glass flask and pour in some liquid vinegar. Then you take a small balloon and pour a few grams of baking soda into it.
The chemical name for that being sodium hydrogen carbonate, just to be precise.
Right, sodium hydrogen carbonate. So you carefully stretch the mouth of the balloon over the top of the flask, making sure the baking soda stays in the floppy part of the balloon for a moment.
So you've now created a miniature closed system.
Exactly. The flask and the balloon are completely sealed off from the outside air. So you set this whole contraption on a digital scale and record the total weight. Let's say it's 150 grams.
And then comes the reaction.
Right. You lift the balloon, the baking soda dumps into the vinegar, and you get immediate violent effervescence. Fizzing, bubbling, foaming.
It's creating carbon dioxide gas.
And in an open bowl, that gas would just float away into the kitchen, and your scale would slowly tick down as the mass escaped.
Because the balloon is sealed over the top.
The gas rushes up and inflates the balloon. You've basically trapped all the escaping coins.
The chemical reaction is raging, the liquid is transforming, the balloon is swelling. But if you look at the digital readout on the scale,
it sits completely frozen at 150 grams. It never wavers.
It is such a profound realization. Matter is incredibly stubborn.
Stubborn.
Yeah, it can transform. It can change state from solid to liquid to gas. It can look completely unrecognizable, but it absolutely refuses to disappear. It refuses to be deleted from the universe.
Which is amazing. But this brings us to a really monumental figure in history. Because while this balloon experiment makes perfect sense to us now, it wasn't always that obvious.
Right at all.
Like the transition from alchemy, where people thought they could magically transmute or destroy matter, to rigorous mathematical chemistry required a genius.
It really did.
Who was the first person to actually look at the math and formalize this stubbornness of matter?
That brings us to late 18th century France, to a man named Antoine Lavoisier.
Antoine Lavoisier.
Yes. He is widely recognized as the father of modern chemistry. Lavoisier was, obsessed with measurement.
Obsessed how?
Well, before him, chemistry was largely qualitative. People notice color changes or smells. Lavoisier made it quantitative.
So he actually started weighing things properly.
Exactly. He used incredibly precise balances to weigh everything before and after a reaction. And in 1789, he formally proposed what we now call the law of conservation of mass.
The law of conservation of mass. Okay, that is the first major pillar of our deep dive today.
His proposition was beautifully simple, yet it basically rewired our entire understanding of the physical world.
What was the specific rule?
He stated that matter can neither be created nor destroyed in a chemical reaction.
Just shuffled around.
Right. The exact phrasing often attributed to his work is that in every operation, an equal quantity of matter exists both before and after the operation. It is the ultimate unbreakable system of cosmic accounting.
Cosmic accounting. I like that. Let's actually look at the ledger because seeing the numbers makes it real for me.
Okay, let's look at an example straight from the source text, example 9.1.
Yeah, let's take an industrial example. Suppose a manufacturing facility is reacting calcium carbonate with hydrochloric acid inside a sealed, pressurized reactor.
Perfect.
So they start by pumping in exactly 4.0 grams of calcium carbonate, and they react it with 2.92 grams of hydrochloric acid.
Let's do the accounting on the input side, what chemists call the reactants.
Okay, a reactant,
You have 4.0 grams plus 2.92 grams.
which gives us a total starting mass of 6.92 grams.
Exactly. That is the total mass entering the system.
Okay, so we have 6.92 grams in the ledger. The reactor fires up, the chemical change occurs.
And when the process is finished, the engineers measure the new substances that have been produced.
Which are called the products.
Right. And they find 1.76 grams of carbon dioxide gas, 0.72 grams of water, and 4.44 grams of a new solid salt called calcium chloride.
So we have three new things. But if we total up those products,
Let's do the math. 1.76 plus 0.72 plus 4.44.
it equals exactly 6.92 grams.
Yes, the mass of the reactants perfectly equals the mass of the products.
So the law of conservation of mass is strictly obeyed.
The books are perfectly balanced down to the hundredth of a gram. You didn't lose any mass, and you didn't create any mass out of thin air.
That is fascinating. But, this conservation is so absolute that it actually creates a new massive problem in my mind.
Oh, what kind of problem?
Well, if matter is strictly conserved and we are literally just shuffling ingredients around, does it just shuffle randomly?
I see where you're going.
Because think about baking a cake, right? I can put in 2 eggs or I can accidentally put in 3 eggs. I'll still get a cake. It might be a slightly denser cake, but it's still a cake. If I take a massive tank of hydrogen gas and a massive tank of oxygen gas, and I just open the valves and let them mix in whatever random quantities I feel like, do I just get some water?
That is the exact logical hurdle that the scientific community faced immediately after Lavoisier published his work.
Really?
Yes, if we are just playing with undestroyable matter, can we combine it in any ratio we want? And the answer is a resounding no.
So the universe does not bake like a sloppy chef.
Definitely not.
Yeah.
There's absolutely nothing random or flexible about how elements combine. And we understand this thanks to another French chemist who was a contemporary of Lavoisier named Joseph Louis Proust.
And Proust provides the second major pillar we are looking at today, the recipe book of the universe.
Proust proposed what is known as the law of constant proportions. Sometimes you'll hear it called the law of definite proportions.
Okay, what did he discover?
His discovery was that in any chemical compound formed by 2 or more elements, those elements combine in a strict, fixed ratio by mass.
A fixed ratio by mass.
And this ratio is absolute, regardless of where the compound comes from, who made it, or how it was synthesized.
Let's go back to our water example, because that makes it easy. Water is H2O, 2 parts hydrogen, 1 part oxygen by volume. But Proust looked at the mass.
Yes, the physical weight of the ingredients.
So what did he find out about water?
Proust realized that if you take pure water, the source is entirely irrelevant. You could scoop water out of the Amazon River and purify it.
Okay.
You could extract water from a million-year-old glacier in Antarctica. You could chemically synthesize water in a high-tech laboratory in Tokyo.
Any water from anywhere.
If you take exactly 9 grams of that purified water and you run an electrical current through it to decompose it back into its base gases, you will always, without exception, get exactly 1 gram of hydrogen gas and 8 grams of oxygen gas.
Wait, always 1 gram of hydrogen to 8 grams of oxygen.
Always. The mass ratio is eternally 1 to 8.
That is so rigidly specific.
It is. If you try to mix, say, 2 grams of hydrogen with 8 grams of oxygen, hoping to get some slightly hydrogen-heavy water,
The universe simply won't allow it.
it won't. 1 gram of the hydrogen will lock together with the 8 grams of oxygen to make 9 grams of water.
And what happens to the leftover 1 gram of hydrogen?
It will just sit there, utterly unreacted, floating around as excess gas. The recipe for water is ruthlessly fixed.
The idea that this applies everywhere in the cosmos is honestly staggering. Like, if we find liquid water on a distant exoplanet 1,000 light years away and we break it down, it will stubbornly adhere to that exact 1:8 ratio by mass.
It has to. If it doesn't, it is literally not water. It is something else entirely.
You know, there's this fascinating historical narrative in the source material that illustrates how ancient people stumbled onto this law long before Proust formally wrote it down.
Yes, the story about cinnabar,
Right. It involves this mineral called cinnabar.
which is a brilliant, vibrant red rock.
Yeah, and in various ancient cultures, particularly in India, where it was known as hingula, it was highly prized.
For centuries, ancient civilizations crushed this rock to use as a vivid red pigment for painting, cosmetics, and decorating sacred objects.
But ancient alchemists were always tinkering, right?
Always.
Over time, they realized that if they subjected this red rock to intense heat, like roasting it in furnaces, it broke down, it decomposed.
And it always decomposed into two very distinct, very intense substances, liquid mercury and yellow sulfur.
And here is where the law of constant proportions reveals itself in antiquity. Through painstaking trial and error over generations, these early chemists figured out the exact mass breakdown of the rock.
Right. They realized that cinnabar, no matter which mine it was pulled from, is always composed of roughly 86.2% mercury and 13.8% sulfur by mass.
But the wild part isn't just that they broke it down and measured it. The incredible leap was that they realized the process was reversible, provided they respected the math.
It's an amazing discovery for that time period.
They discovered that if they took pure liquid mercury and pure sulfur and ground them back together in that exact 86 to 13 percentage, they could artificially recreate cinnabar from scratch.
They could actually manufacture the red rock. They essentially reverse engineered a geological mineral using the unwritten law of constant proportions.
Although I do feel obligated to point out that this was a spectacularly terrible idea for an ancient DIY project.
Oh, without a doubt.
Mercury is a potent neurotoxin. Grinding liquid mercury and sulfur together by hand in an open mortar and pestle is basically a recipe for severe heavy metal poisoning.
Yeah, health and safety standards in ancient alchemy left a lot to be desired.
The extreme toxicity is probably the only reason this didn't become a widespread, everyday craft.
Very true. But scientifically, their dangerous work proves the point beautifully. A compound always contains the same elements combined in a fixed ratio by mass.
The universe operates on strict blueprints.
Mm.
So let's look at the puzzle pieces we have on the table right now. Lavoisier tells us that matter is conserved, meaning you cannot create or destroy the fundamental ingredients.
Right.
And Proust tells us that those ingredients always combine in strict, unchangeable recipes, like the 1:8 ratio of water. We know that these laws are true because we can measure the weights.
We can prove it on a scale.
But science isn't just about knowing that something happens, it's about knowing why it happens. Why are these laws so rigid? Why does water have to be 1:8? Why can't I just smoothly blend matter together in any proportion?
This is the moment where human understanding makes a massive quantum leap.
Because for a while they didn't know, right?
Right. For a couple of decades, scientists were totally stuck. They had the ledgers from Lavoisier, they had the recipes from Proust, but they lacked the mechanical explanation.
The underlying mechanism.
To answer the why, we have to move to England, to the year 1808, and look at the work of a brilliant mathematics and chemistry teacher named John Dalton.
John Dalton. He essentially looks at the work of Lavoisier and Proust, and he realizes that the only way their laws make sense is if matter isn't some smooth, continuous paste, but rather something granular.
Precisely. To really understand Dalton's breakthrough, you have to understand the prevailing philosophy of the time.
What were people thinking back then?
Well, going all the way back to Aristotle, many philosophers believed that matter was continuous, that you could take a drop of water and divide it in half infinitely, forever, and it would always just be a smaller smear of water.
But Dalton said no.
Dalton said no. He proposed his atomic theory, laying it out in a series of foundational rules or postulates.
Think about this like building blocks. Imagine the scientific world before Dalton. You have Lavoisier and Proust. They are scientists studying massive, complex Lego castles, which represent our chemical compounds like water or cinnabar.
That's a great visual.
So Lavoisier, the accountant, realizes, hey, if I smash this castle apart, the pile of loose blocks weighs exactly the same as the fully built castle. He discovers conservation of mass.
The total plastic is conserved.
Right. Then, priest comes along, looks at the instruction manuals for the castles, and says, hey, no matter who builds this specific castle, whether it's a kid in London or a kid in Tokyo, the blueprint always requires exactly 1 red block for every 8 blue blocks.
So he discovers constant proportions.
Exactly. But they're still just looking at the big picture, the microscopic world. Dalton was the one who finally walked up, picked up a single tiny plastic brick, and said, the reason your rules work is because the universe is made of these individual, indivisible blocks.
That is a phenomenal conceptual map of what happened. Dalton provided the microscopic mechanism for macroscopic laws.
Let's look at the specific rules he proposed.
Okay, first, he stated that all matter is made of very tiny, indivisible particles called atoms. They cannot be created, and they cannot be destroyed in a chemical reaction.
Which instantly solves Lavoisier's mystery.
It does.
If the universe is built out of indestructible little beads, then of course you can't lose mass in a fire or a chemical reaction. You aren't destroying the matter, you are just snapping the beads apart and rearranging them into a new shape.
Yes. Second, Dalton stated that atoms of a specific given element are absolutely identical in mass and chemical properties.
Meaning every single atom of pure gold in the universe is identical in mass to every other atom of pure gold.
Exactly. To use your analogy, a red Lego block is always exactly the same size and weight as every other red Lego block.
Got it. And the third rule.
Third, atoms of different elements have different masses and chemical properties. An oxygen atom is fundamentally different in mass and behavior than a hydrogen atom.
So a red block is fundamentally different from a blue block.
Right. And finally, the rule that explains Proust. Dalton stated that atoms combine in the ratio of simple whole numbers to form compounds.
Oh, because you can't have half an atom? You can't snap half a Lego block onto a structure. You either use 1 whole block or 2 whole blocks. So when they combine, they have to combine in these rigid, whole number mathematical ratios, which perfectly explains why the mass ratios are always constant.
Exactly. To apply this to a real chemical example, think about magnesium metal burning in the air. It's a fairly common industrial reaction.
What happens when it burns?
When magnesium burns, it reacts with oxygen to form a fine white powder called magnesium oxide. Dalton's theory illuminates what is happening behind the curtain of the flames.
The atoms of solid magnesium weren't destroyed by the fire.
And the atoms of oxygen gas weren't destroyed either. The heat simply provided the energy to break their previous arrangements, allowing the magnesium atoms to snap together with the oxygen atoms in a simple 1-to-1 whole number ratio.
Building a brand new architectural structure, which is the white powder.
Exactly.
So we've established that atoms are the building blocks of everything. We have our atomic Legos, we know they are indestructible, and we know they combine in fixed ratios. But this begs an incredibly obvious question. How do they snap together?
The mechanic of bonding.
Yeah, because if I put a pile of red blocks and a pile of blue blocks in a box and just shake it, they don't magically build a castle. What is the clutch power of these atomic blocks? Why do they stick to each other at all? What is the motivation for an atom to bond?
Now we are drilling down into the real engine of chemistry. The invisible drive behind every reaction, every fire, every rusting piece of iron, and every biological process in your body.
It all comes down to what?
It all comes down to one single, universal motivation: the relentless pursuit of stability.
Atoms are trying to become stable.
Yes, atoms are inherently restless. And for an atom, stability has a very specific quantifiable definition.
What is it?
It revolves around the electrons that orbit the nucleus of the atom, specifically the electrons in the outermost layer, which we call the valence shell.
Valence shell, okay.
Stability means having a perfectly full outer shell. For the vast majority of elements we interact with, a full outer shell means having exactly 8 electrons. This is known in chemistry as the octet rule.
An octet. 8 electrons.
There is a tiny exception for the very smallest, lightest atoms in the universe, like hydrogen and helium.
Because they're so small.
Right. They only have one single shell, the innermost layer, and that layer only has room for 2 electrons. So for them, stability means a duplet of 2. But for almost everyone else, the magic number is 8.
It sounds almost like a spiritual state for an atom. Achieving enlightenment is getting 8 electrons in your outer shell.
It's actually a great way to think about it. And there are a few elements that are born enlightened, so to speak. We call them the noble gases.
Like neon or argon.
Right. They naturally possess exactly 8 electrons in their outermost shell. Because their octet is perfectly full, they are completely stable, they are perfectly content.
So they don't react with anything.
They have zero thermodynamic motivation to react, bond, or interact with any other element. They are inert. They just float around, ignoring the rest of the chemical world.
Must be nice, but the vast majority of the periodic table isn't so lucky.
The vast majority are deeply unfulfilled.
An atom of oxygen might only have 6 electrons in its outer shell. An atom of sodium might only have 1.
So they're stressed out.
Because they don't have that full octet of 8, they exist in a state of elevated energy. They are stressed, restless, and chemically reactive. When atoms bump into each other and combine to form a compound, what they are actually doing is negotiating a way to complete their octets.
So atoms are basically trying to lower their stress levels by forming relationships.
That is the thermodynamic reality. When they find a way to complete their octets together, the total energy of the new combined system drops drastically compared to the high energy of the individual restless atoms.
And in physics, a lower energy state always equals greater stability. Always. And the invisible force that holds them together once they've negotiated this relationship, that attraction, is what we call a chemical bond.
Okay, so if I'm a restless atom and I'm stressed out because I only have 7 electrons in my outer shell, and I desperately need an 8th electron to reach this state of stability and lower my energy, how do I get it? Do I just steal it? Do I borrow it?
You have two primary lifestyles, two main strategies to achieve that octet.
Okay, what are they?
Strategy number 1 is a compromise, sharing your electrons with another atom. Strategy number 2 is more dramatic. The outright transferring of electrons, either giving yours away entirely or aggressively stealing someone else's.
Sharing versus transferring. Okay, think about 2 roommates who move into a bare apartment. Neither of them has enough money to buy a television on their own.
I like this analogy already.
Roommate A has half the cash. Roommate B has half the cash. If they act selfishly, neither gets a TV. But if they pool their money, they can buy one television, put it right in the middle of the living room, and share it.
They both benefit.
Right. Neither one purely owns it, but they both get the full benefit of watching it. And because they share this vital asset, they are bonded together. They have to stay living in the same apartment to keep access to the TV.
That is a flawless model for what we call a covalent bond. Covalent bonding is the sharing of electrons. And when atoms bond covalently, they form what we call distinct molecules.
Let's map the roommates onto a real molecule to see how it works.
Let's use water, H2O again. You have an oxygen atom in the center. Oxygen naturally has 6 electrons in its valence shell. It is stressed.
It desperately needs 2 more electrons to reach the stable octet of 8.
Right. Then you have 2 hydrogen atoms floating nearby. Each hydrogen atom has only 1 electron. But remember, hydrogen is tiny. It only needs 2 electrons to fill its inner shell and reach stability.
So each hydrogen needs 1 more.
Exactly.
So everyone is broke and needs a TV.
Exactly. So they negotiate a compromise. The central oxygen atom approaches one of the hydrogens and essentially says, I will let you overlap your shell with mine and share one of my electrons, provided you let me share your 1 electron.
And they lock together.
Now, the hydrogen has access to 2 electrons, so its shell is full, its energy drops, it is stable, and the oxygen gets to count that shared electron toward its own total, bringing it up to 7.
It's close, but the oxygen still needs 1 more to reach 8.
So it turns to the second hydrogen atom and makes the exact same deal on the other side.
That makes perfect sense. By sharing electrons with 2 different hydrogens, the oxygen now gets to count 8 electrons in its outer shell. It achieves its octet.
The hydrogens achieve their duplets, their total energy plummets, and they become a stable, independent unit, a single neutral molecule of water. That is covalent bonding.
Okay, so that's the sharing lifestyle. What about the second strategy, the transferring?
Ionic bonding.
If covalent is a roommate compromise, this second lifestyle feels much more intense. Let's say roommate A moves into an apartment and they own 2 televisions. Roommate B moves in and they own 0 televisions.
A very imbalanced living situation.
Instead of putting them in a shared living room, roommate A simply hands one of the TVs over to roommate B. Here, take it to your bedroom, it's yours.
Wow, generous.
Roommate A loses a TV, roommate B gains a TV. But because of this massive life-changing gift, roommate B feels a profound magnetic sense of debt and loyalty to roommate A, and that intense psychological attraction keeps them bonded together in the apartment.
It's a dramatic scenario, but mathematically and physically, it describes ionic bonding perfectly.
So no sharing at all.
None. Ionic bonds involve the outright transfer of electrons.
Right.
And because they are moving electrical charges around, ionic bonds don't form neutral, independent molecules. They form charged particles called ions.
Let's look at the classic example. Table salt. Sodium chloride, NaCl.
Let's examine the stress levels of these two atoms before they meet. Sodium is a highly reactive, incredibly dangerous metal. If you drop pure sodium into water, it explodes violently.
Why is it so angry?
Because sodium has exactly one single lonely electron floating in its outermost valence shell. To reach stability, it would either have to find 7 more electrons, which is energetically nearly impossible,
Mm.
or it could do something drastic. It could just violently eject that one outer electron entirely. If it loses that one outer electron, the shell underneath it becomes the new outermost shell, and that inner shell is already perfectly full with 8.
Oh, so the sodium atom is utterly desperate to throw this electron away. It is looking for anyone to take it.
Now look at chlorine. Pure chlorine is a toxic, lethal green gas.
Also very dangerous.
Very. Because a chlorine atom has 7 electrons in its valence shell. It is agonizingly close to stability. It is frantically hunting for one single electron to reach the magic number of 8.
So you have sodium, desperate to discard an electron, and chlorine, desperate to steal one. When these two wildly dangerous elements get near each other, it's a perfect match.
There's no negotiation, no sharing. The sodium atom outright transfers its one electron entirely over to the chlorine atom.
Just hands it over.
But here is the critical mechanism. Electrons are negatively charged particles. When the sodium atom loses that negative electron, the mathematical balance of the atom changes.
Because it lost a negative charge.
Right. It now has more positive protons in its nucleus than negative electrons orbiting it. The entire sodium atom suddenly takes on a net positive electrical charge. It becomes a positive ion, which scientists call a cation.
A cation, okay. And the chlorine atom.
The chlorine atom accepted that extra negative electron, so its mathematical balance shifts the other way. It takes on a net negative electrical charge. It becomes a negative ion called an anion.
So the transfer of the electron creates a positively charged sodium cation and a negatively charged chlorine anion.
Exactly. And what is the fundamental law of electromagnetism?
Opposites attract. Positive and negative charges attract each other powerfully.
That intense, invisible electrostatic force pulls the positive sodium and the negative chlorine tightly together.
Yeah.
That magnetic-like attraction is the ionic bond.
And miraculously, when these two dangerous explosive elements bond this way, their energy drops so radically that they form stable, delicious, harmless table salt.
That transformation is really mind-blowing. Now, there is a small layer of complexity here when we talk about ions.
Oh, what's that?
Usually, we think of an ion as a single atom, like one sodium atom that has gained or lost an electron. But sometimes, atoms form squads.
Squads.
Yes, these are called polyatomic ions. Sometimes a small group of atoms will covalently bond together and share electrons to form a little cluster, but the cluster as a whole still has an imbalance of electrons.
So the entire group acts together as a single charged unit.
Right. A common example is the ammonium ion. It's one nitrogen atom and 4 hydrogen atoms covalently bonded into a tight group, but the whole group carries a positive 1 charge.
Or the sulfate ion, right?
Yes. Sulfate is 1 sulfur and 4 oxygens acting together with a negative 2 charge. You treat the whole squad as a single puzzle piece when building compounds.
Okay, so we have these two vastly different microscopic lifestyles. Covalent sharing, which builds independent molecules, and ionic transferring, which builds charged ions locked together by magnetic attraction.
You've got it.
But if I have a pile of a covalent compound, like sugar, on one table, and a pile of an ionic compound, like salt, on another table, does this invisible microscopic difference actually matter in the real world? Like, do they behave differently?
They behave incredibly differently, and you can actually test this with very simple physical experiments, primarily looking at solubility and electrical conductivity.
Oh, let's start with solubility. What happens when we try to dissolve them?
Solubility is all about the interaction between the substance and the liquid you drop it into. Let's take our ionic compound, table salt. If you drop salt into pure water, it dissolves effortlessly. It vanishes into the liquid.
But if you take that same salt and drop it into an organic solvent, like kerosene or gasoline,
it just sits there at the bottom of the glass.
Yep.
It completely refuses to dissolve.
Why is water able to dismantle the salt, but kerosene can't?
It comes down to the electrical charges. Remember, the salt is held together by the strong positive and negative attraction of the ions.
Right.
Water is what we call a polar molecule. The oxygen end of a water molecule has a slight negative charge, and the hydrogen ends have a slight positive charge.
So water molecules act like billions of tiny, weak magnets.
Exactly. When you drop salt into water, these tiny water magnets swarm the salt. The negative end of the water pulls on the positive sodium, and the positive end of the water pulls on the negative chlorine.
And eventually, the water's pull overcomes the ionic bond, tearing the salt apart ion by ion, dissolving it.
But kerosene doesn't have those magnetic pulls.
Ah, kerosene is nonpolar.
Exactly.
Ah,
It has no electrical charge to pull the ions apart, so the salt remains solid. Covalent compounds, however, like camphor or certain waxes, often behave the exact opposite.
because they don't have those extreme charges.
Because they are made of neutral molecules sharing electrons, they don't interact well with the magnetic pull of water, but they dissolve beautifully in neutral solvents like kerosene.
So their microscopic bonds literally dictate what they can dissolve in.
That's cool. What about electrical conductivity? You said the physics gets really visual here.
Electrical conductivity is the test that truly proves the existence of ions. Imagine setting up a simple circuit. You take a glass beaker, you drop in 2 metal electrodes, and you wire them up to a 9-volt battery and a small light bulb.
Okay, little science fair setup.
If you pour pure distilled water into the beaker, the circuit is broken. The light bulb stays completely dark. Pure water is a terrible conductor of electricity.
What if I dissolve a covalent compound into the water? Let's say I dump a cup of sugar into the beaker and stir it up.
The sugar dissolves, but the light bulb remains entirely dark. Covalent molecules are electrically neutral. They have no charge.
But what if I dissolve an ionic compound? What if I dump in our table salt? The moment the salt dissolves, the light bulb blazes to life. The saltwater solution conducts electricity flawlessly.
Wait, why? What is happening in the water?
Electricity is simply the flow of electrical charge. When the salt dissolves, remember what the water is doing. It is tearing the salt apart into billions of free-floating, positively charged sodium cations and negatively charged chlorine anions.
So you now have a liquid teeming with mobile electrical charges.
When you turn on the battery, these charged ions act like tiny, microscopic ferry boats. They physically carry the electrical current through the water from one electrode to the other, bridging the gap, completing the circuit, and lighting the bulb.
And because covalent sugar has no charges, it has no ferry boats.
Exactly.
That makes perfect sense. But there is a crucial caveat here from the source text that I want to explore. Ionic compounds are made of these charged ferry boats, but if I take a dry, solid block of pure table salt and I jam the 2 electrical wires into the solid block, the bulb does not light up.
It does not.
The solid salt won't conduct electricity. If it's made entirely of charged ions, why won't it carry the current?
This is the beautiful quirk of physical chemistry, and it reveals the true 3D architecture of ionic compounds.
Okay, unpack this for me.
When we talked about covalent bonds, we said they form independent molecules, like a single loose car driving down a highway. But ionic compounds don't form loose molecules.
Because they just keep attracting each other.
Right. When a positive sodium ion and a negative chlorine ion attract each other, their magnetic pull doesn't just stop there. That sodium ion will attract other chlorine ions from all sides, top, bottom, left, right.
And those chlorines will attract more sodiums. It builds out in every direction.
Exactly. They lock together into a massive, rigid, three-dimensional grid that extends indefinitely. We call this a crystal lattice.
Oh, crystal lattice.
A single grain of table salt is a crystal lattice containing trillions of ions locked in a perfectly alternating grid. In a solid block of salt, the ions are trapped in this rigid scaffolding. They cannot move.
And if the charges cannot move, they cannot act as ferry boats. No movement equals no electricity.
Precisely. To conduct electricity, the charges must be mobile. When you dissolve the salt in water, the lattice is destroyed and the ions are free to swim around.
Is there any other way to break the lattice?
The only other way to make salt conduct electricity is to heat it up to incredibly high temperatures until it literally melts into a liquid. Molten salt.
Wow, molten salt.
The intense thermal energy shakes the crystal lattice apart, the ions become a fluid, mobile soup, and suddenly, the molten liquid conducts electricity perfectly.
So we have these 2 profoundly different architectures. Covalent compounds are independent, standalone molecules. Ionic compounds are massive, infinite 3D crystal grids.
Right.
Because their structures are so fundamentally different, chemists actually have to use different mathematical frameworks when calculating their microscopic mass.
Yes. If you want to calculate the mass of a microscopic chemical structure, you have to use the right terminology based on its architecture. We use 2 different terms, molecular mass and formula unit mass.
Let's start with the easier one, molecular mass.
Molecular mass is used strictly for covalent compounds. Because covalent compounds exist as distinct independent molecules, The boundary of the object is perfectly clear.
You can isolate one single molecule of water or one single molecule of carbon dioxide and just weigh the atoms inside it.
Let's walk through the calculation. How do
Yeah.
we find the molecular mass of carbon dioxide, CO2?
Okay, you look at the chemical formula and you look at the atomic mass of the elements involved, which are measured in atomic mass units, denoted by a lowercase u.
Right. One molecule of CO2 has exactly one carbon atom and two oxygen atoms. The atomic mass of carbon is 12U. The atomic mass of oxygen is 16U.
So we just do the basic arithmetic. We have one carbon, so that's 12. We have two oxygens, so that's 16 times 2, which is 32. We add them together. 12 plus 32 equals 44.
Exactly. The molecular mass of CO2 is 44U. It is the literal mass of one specific isolated molecule. But you cannot do this with ionic compounds.
Because there is no such thing as a single isolated molecule of salt.
Exactly. If you ask a chemist for the molecular mass of a salt crystal, the question doesn't make sense. A salt crystal is an endless lattice. Where does the molecule begin and end? It doesn't.
You might have a crystal with 1 billion sodiums, or a crystal with 1 trillion sodiums.
Because it's an infinite grid, we use a different concept. Formula unit mass.
A formula unit, what does that actually mean?
A formula unit is simply the lowest, simplest whole number ratio of the ions within that massive crystal lattice. You aren't weighing the whole crystal, you're just weighing the basic repeating pattern.
Think of it like this. Covalent compounds are like individual cars driving down a highway.
Right.
You can easily pull one specific Honda Civic over onto a weigh station and find the weight of that one discrete car. That's molecular mass.
Right, the discrete car.
But ionic compounds are like a massive infinite traffic jam where millions of cars are welded together bumper to bumper in a solid block. You can't possibly weigh the entire traffic jam, and you can't snap one car off to isolate it.
So what do you do?
If you look closely at the jam, you notice a repeating pattern. For every 2 red sedans, there's exactly 1 blue truck. That pattern repeats endlessly. So instead of trying to weigh the whole thing, you just calculate the weight of that one simple repeating ratio. 2 sedans and 1 truck. That representative segment is your formula unit.
That is a perfect visualization. And the math to calculate the mass is exactly the same. We just use a different term to respect the physical reality of the lattice.
Let's do the math for an ionic compound then.
Let's take sodium oxide. The formula is Na2O. The crystal lattice is huge, but the simplest repeating pattern, the formula unit, is 2 sodium ions for every 1 oxygen ion.
So we tally it up. The atomic mass of sodium is 23U. The atomic mass of oxygen is 16U.
We have 2 sodium, so 23 times 2 is 46. We add the 1 oxygen, which is 16. 46 plus 16 equals 62. The formula unit mass of sodium oxide is 62U.
All right, we have built an incredibly solid foundation of how matter works. We know mass is conserved. We know compounds form in strict ratios. We know Dalton's atoms are the indestructible Lego blocks making this all possible. And we know they bond covalently or ionically to find stability.
We've covered a lot of ground.
But before we conclude this deep dive, we have to address the elephant in the room. We have to talk about the moment human science broke the ultimate rule.
Yes. We have to talk about the breaching of the atom itself.
John Dalton's very first postulate, the bedrock of his entire theory in 1808, was that atoms are tiny, indivisible, indestructible particles. You cannot break them down.
And for over a century, that was treated as absolute gospel, because in the realm of normal chemistry, it is entirely true.
Right. In every scenario we have discussed today, a campfire burning, a combustion engine running, iron rusting on a bridge, baking soda erupting in vinegar, the atoms themselves are completely unharmed.
Chemical reactions are merely the breaking and forming of the electrostatic bonds between the atoms. The electrons shuffle around, but the core of the atom, the nucleus, remains utterly pristine and untouched.
But the universe has deeper layers. Later, physicists discovered that Dalton was wrong in the absolute sense. The atom is not a solid, indivisible bead.
It has an internal structure. It has a dense core made of protons and neutrons, held together by something called the strong nuclear force. And if you know how, you can crack that core wide open.
This takes us out of the realm of chemistry and into the realm of nuclear physics.
Right. Scientists discovered that certain heavy, unstable elements like uranium can undergo a process called fission. If you fire a stray neutron into the nucleus of a uranium atom, the nucleus becomes intensely unstable.
It wobbles, it deforms, and eventually the strong nuclear force fails.
The atom literally snaps in half, splitting into 2 completely different lighter elements.
You have destroyed the original atom. You have transmuted matter.
You have done what the alchemists dreamed of, but at the atomic level. And when that nucleus splits, It releases energy, but it is not the gentle warming energy of a campfire.
No, it's not.
The energy released when the strong nuclear force is broken is astronomically, unfathomably larger than the energy released by breaking a chemical bond.
The discovery of this nuclear energy completely altered the trajectory of human history. It is a force so potent that it powers modern civilization.
We use controlled nuclear fission to boil water, create high-pressure steam, drive massive turbines, and generate electricity for millions of homes without burning fossil fuels.
We use it to power deep space probes exploring the outer edges of the solar system, where solar panels are useless.
It represents a monumental leap in human capability, and it requires immense scientific infrastructure to harness safely and peacefully.
There is a notable historical factor mentioned in our focus on this topic, Dr. Raja Ramana, who is widely considered the father of the Indian nuclear program.
Yes, Dr. Ramana was a brilliant physicist who envisioned the peaceful developmental applications of this staggering power.
He was instrumental in building the scientific community, the research reactors, and the infrastructure that allowed India to harness atomic energy for national growth. His work really exemplifies the transition from discovering a terrifying new physical reality to engineering it for human benefit.
It proves that science is an ever-evolving narrative. We take the rules established by giants like Lavoisier and Dalton, we rely on them because they work for 99% of our daily lives, but we remain curious enough to discover the extreme conditions where those rules finally bend or break.
Let's pull all of these threads together. Think about the physical world around you. Think about the water you drink, the iron in your blood, the plastic in your phone.
It's all connected.
We started today by proving that the matter making up those things is ancient and conserved. Lavoisier showed us the cosmic ledger never loses a single gram.
We saw through proofs that this matter is organized into strict, unchanging mathematical recipes.
Dalton gave us the mechanical explanation, the indestructible atomic blocks.
We watched those blocks desperately seek stability through the octet rule, either sharing electrons like roommates to form covalent molecules, or transferring them to build massive electrically conductive ionic grids.
You now possess the foundational blueprints for how the material universe operates at a microscopic level.
But I think you had one more puzzle for the listener.
I do. I want to leave you with a final thought, a puzzle to mull over. We spent the first half of this deep dive proving Lavoisier right. In every chemical fire, in every reaction, mass is strictly conserved. If you start with 6.92 grams, you end with 6.92 grams. The ledger always balances.
Always.
But think about what we just discussed in the final segment regarding nuclear fission. When we split the nucleus of an atom to generate that city-powering energy, something incredibly strange happens to the math.
A discrepancy in the ultimate ledger.
Yes. In the 1900s, a physicist named Albert Einstein proposed an equation, E mc Coffeal. Energy equals mass times the speed of light squared.
What this equation tells us is that mass and energy are not two different things. They are two sides of the same coin.
During nuclear fission, when that atom splits and releases that apocalyptic amount of energy, if you were to carefully weigh the two new broken pieces of the atom, you would find that they weigh slightly less than the original atom did.
The mass does not balance.
A tiny fraction of the physical mass has literally vanished from the universe. It didn't float away as a gas. It didn't escape the sealed bag.
The mass physically ceased to exist as matter.
And transformed directly into the pure, blinding energy that powers our cities and our stars. So here's the question for you to take with you. Lavoisier gave us the law of conservation of mass, and it governs our everyday world perfectly. But when we look at the stars and when we split the atom, what does it mean for our understanding of reality that the physical substance of the universe can simply dissolve into pure energy? Where is the line between a physical object and the energy it contains?
That is the beautiful frontier of physics. The deeper you look, the more profound the mysteries become.
Thank you for joining us on this deep dive. Keep questioning the invisible architecture of the world around you. We'll see you next time.